Okay, so welcome to section 3.2. Title of section 3.2 is Basic Differentiation Rules and Rates of Change. Okay, so basically we're going to cover two things in the second section, some basic rules for differentiation and some applications of the idea of a rate of change. The major goal in sections 3.2 through section 3.4, the major goal of these three sections is to never use the limit definition again. Okay, so that limit definition that we learned in section 3.1 is great because it always works no matter what, but it's also slow, it's also cumbersome, and it's also prone to mistakes because there's a lot of moving parts. So what we would like to do is we would like to come up with a bunch of rules that we can use for taking derivatives, for doing differentiation, so that we don't have to have that limit, and so we don't have to use that limit definition. Here's the problem, though. We have to memorize a bunch of rules, because if you run into something, and your job is to take the derivative of a function, and you do not have a rule for the derivative of that function, if you don't have a rule for it, how are you going to take that derivative? And if you don't have a rule for it, you'll have to use the limit. And I don't want to use the limit. So in this section, we're going to take a look at finding the derivative of a function using a constant rule, power rule, constant multiple rule, sum and difference rules, sines and cosine functions, exponentials, and then we'll take a look at some applications. That's a lot because it's a big section. Okay? So in this section, we're going to take a look at several differentiation rules, so we don't have to use the derivative. Okay? Now, these are not magic. These are just, hey, we noticed that every single time we did the limit rule, the following happened. And so since every time we did the limit, this happened, then that's what we're going to use. We're going to use the shortcut. It's sort of like back when you learned this. The quadratic formula. Where did that come from? Well, guys were solving, people were solving quadratic equations, and they noticed that, hey, look, they always turn out to be this. So why don't we just do the shortcut and go straight to there? Okay, this came from completing the square. In case you're wondering where that came from. Okay. All right, so while we occasionally might still need to use that limit definition, but we don't want to have to use it if we don't have to. So here's our first rule. It's called the constant rule. And it says the derivative of constant is always 0. That is, if c is any real number, then the derivative of c is equal to 0. Now, just as a side note, you'll notice right here, this is that notation I was telling you about, where we have the operator on the left, and it says take the derivative of a constant, and that derivative is equal to 0. Did you notice that this operator notation, does not exist on the right-hand side of that equal sign because it tells you what to do. It's an operator. Mathematical operators go away when you perform the operation. What's 3 plus 2? Well, 3 plus 2 is 7. Where did the plus sign go? Why is there no plus sign on the right-hand side? It is a mathematical operator that tells you what to do. And when you perform that operation, the operator goes away. So if this is an operator that tells me to take a derivative, when I took the derivative, when I did the differentiation, the operator goes away. All right. Now, the constant rule is always 0. Makes sense if you think about what a constant means. If you have the function f of x is equal to c, that's just a horizontal line. And what is the slope of a horizontal line? The slope of the horizontal line is always 0. So if m is always 0 for any point on that line, that would imply that the derivative must also always be 0. Right? Our next rule is the power rule. The power rule says that if n is a rational number, remember, a rational number is a number that can be created by taking two integers and making a ratio out of them, and the denominator can't be 0, obviously, then the function f of x is equal to x to the nth is a differentiable function, and the derivative of x to the nth is n times x to the n minus 1. 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 This is one of the ones that we will be using so much that it would become just ingrained in your brain. Okay? The derivative with respect to x of x to the 7th. N, 7. 7 times x to the 6th. N times x to the n minus 1. N times x to the n minus 1. Okay. Sometimes some books will write this as a separate rule, but essentially this is just the power rule. It's the power rule when n is equal to 1, because there's a little 1 right there, and we don't write it. And we really should write this as 1 times x to the 0. But for any value of x that matters, x to the 0 is equal to 1. So we just say the derivative of x is equal to 1, which also makes sense if you think about this geometrically. If you have the function f of x is equal to x, that's the line passing through the origin. And what is the slope of this line? The slope of this line everywhere is 1. And since the slope is always 1 for all values of x, then f prime better be 1. Okay. All right, here we go with some examples. Okay. What is the derivative of y to the 7th? Okay. All right. Now, if you thought 0, you're almost right. You get maybe half credit. Okay. Because just simply writing down 0 because you say, oh, look, it's a constant. The derivative of a constant is 0. It's incorrect because you have not labeled this and told me what this is. You would be correct if you said y prime is 0. You would also be correct if you said that the derivative of y with respect to x dy dx is equal to 0. You would be incorrect if you wrote anything else. Right? If you just write down 0, that's not right, because what is 0? We need to label it. Because things are getting more complicated, because we are going to have problems where we will have a function and the function's derivative being used in the same solutions. We need to label things to make sure we keep them separated, so we know which one we're talking about when we're talking about it. Okay? All right. Moving on to our next example. F of x is equal to 0. What is the derivative of that? Well, 0 is a constant, so that means that its derivative, f prime of x, is also equal to 0. Okay? So I'm taking derivatives. My job is to take a derivative. Take a derivative, take a derivative, take a derivative. Okay? Here we go. I have a function here whose name is s. The variable is t. It's equal to -3. -3 is a constant. That means that s prime of t is equal to 0. Okay? So I'm taking the derivative of a constant. Now I'll move on to some more complicated ones. What is the derivative of f of x when f of x is equal to x cubed? Derivative of f of x is equal to x cubed can be found because this is a rational number exponent. And since that is a rational number exponent, I can take its derivative using the power rule. And then I will get that f prime of x is equal to n times x to the n minus 1, or 3x squared. So f prime of x. Okay? Now I know at least one person out there is thinking, could I do this? Could I say that y prime is equal to 3x squared? There are some people that might let that slide. I would say that's wrong. Simply because this guy has a name. The name of this function is f. That means its derivative is f prime. Okay? If the function had a different name, like y, then it could be y prime. Similarly, I would argue that you probably are not being accurate if you say something like that, dy dx. We save the y prime and the dy dx for when the function was given to us as y equals. If it's given to us with a name, we use its name in the derivative. Okay. All right, here we go. I have g is equal to the cube root of x. I've got a problem. This is a problem you're going to see a lot of. I don't have a rule for the cube root of x. I essentially have three rules right now. Here are my three rules. My three rules are that the derivative with respect to x of a constant is 0. The second rule that I have is that the derivative with respect to x of plain old x is equal to 1. And the third rule that I have is that the derivative with respect to x of x to the nth is equal to n times x to the n minus 1. And if I don't have one of these three sitting in front of me, either a constant, a plain old x, or an x raised to the n, then I cannot use a shortcut and I have to use limits. Now I don't want to use limits because I'm lazy. So I need to find a way to rewrite that so it looks like one of those three up there. What I'm hoping is you're seeing the same thing that I'm saying, is that we can rewrite g of x as x to the 1/3. Cube root 1/3, 1/3 cube root. Right? And since we can rewrite it as that, now we have a general power rule we can use. And so we can say then that g prime of x is going to be 1/3 times x to the 1/3 minus 1. Clean that up a little bit. We're going to get 1/3 times x to the negative 2/3. That's going to be our g prime. Now this may or may not be correct. So I'm just going to highlight it here. This may or may not be correct depending on the directions. What you'll find is in some of the directions, they will say that your final answer cannot contain negative exponents. Okay? So they don't want this. So what are we going to have to do to get rid of negative exponents? Well, negative exponents means to move that to the denominator. So then we would say that g prime of x is equal to 1 divided by 3 times x to the 2/3. Okay. Now occasionally you will see that it is not preferred to even have fractional exponents. So they might want you to rewrite this as 1/3 times the cube root of x squared. So which one of these is the correct one? The highlighted yellow, the highlighted pink, or the highlighted blue? I don't know. All of them are mathematically equivalent. It just depends on what do the directions say. If the directions do not specify, I would leave it at the yellow. Okay? The challenge that we have with the yellow is depending on how sloppy your writing is, some people might think that this is already in the denominator, and we don't want that. Okay? So if you're going to leave it that way, make sure you write it right. It's also considered bad form to mix fractions and negative exponents, which is why some people will prefer this form, the pink form. And then you will occasionally get people who are, old school and they want the highlighted blue one there at the end. Okay? It just depends. And make sure you read the directions. All right, here I go again. I've got another one that I don't have. I don't know what to do with this one because this is again not a constant, not a plain old x. Okay, so it's not a constant, not a plain old x. It's not an x to the nth. So either I use limits or I find a way to mathematically rewrite this. So I'm hoping you're seeing the same thing I'm seeing, that we can rewrite this as x to the negative 2. Okay? And then when I take the derivative, I'm going to get the dy dx, the derivative of y with respect to x, will be negative 2 times x to the negative 2 minus 1, which gives me negative 2x to the negative 3. Now, I'll tell you that in my experience, this right here is the single most common mistake that I will see. People will mistakenly say that negative 2 minus 1 is negative 1, and that will be the incorrect exponent, right? So just be careful with that. Make sure that when you do your subtraction, negative numbers actually get, in terms of absolute values, get larger when you subtract 1. Okay? It would also not be incorrect, depending on the directions, to have to or to need to rewrite this one as this. And that would be our dy dx. You would not be incorrect if you called this y prime as negative 2 over x cubed. But like I said before, I'm not a huge fan of that because my handwriting is sloppy enough that I've lost it. Not that I would say it's wrong, it's just I don't like to use it because I lose y primes, and when I lose y primes, I get wrong answers, and it just frustrates me. Okay? All right, we got some more rules coming up here, but those will begin the next part of this video. We're already at 15 minutes, so I'm going to stop it here. We'll come back and develop some more rules.